Hello students, now we are going to discuss the two important topics, that is hyperconjugation and steric effect related to electronic displacement in organic compounds. These two effect is very important. Hyperconjugation, it is the stabilizing the molecule, that is organic compound, by the interaction of electrons in a sigma bonded electrons with an adjacent empty orbitals, either p orbitals or attached to pi orbitals. That means it is an interaction that is also called as sigma p interaction, or it is called sigma p pi interaction. Sigma p interaction or sigma p pi interaction results formation of pi bonds, or delocalization of pi bond takes place due to the involvement of sigma bonded electron, that either CH bond or CC bond, but CH bond is more reactive than CC bond in compared to delocalization involvement. This bonded electron, sigma bonded electron, involved in pi bond conjugation with adjacent carbon atoms. That's why it is the interaction of sigma p. Sigma means CH bond or CC bond with vacant p orbital of adjacent carbon atom or pi orbital of adjacent CC bond, forming new molecule, new types of system, develop a new type of system, more stable molecular orbital, produce more stable molecular orbital. Let us discuss some examples. Here hyperconjugation, here what happens, suppose this is the case, this is your called ethyl carbocation. Here ethyl CH bond, this is called alpha. This alpha CH bond it is converted to, it involved in the interaction with adjacent vacant p orbital of carbon atom. As carbon carrying plus charge, it has one vacant p orbital. This vacant p orbital overlap with the sigma bonded electron, sigma bonded orbitals, forming pi bond. It is also symbol is same as resonance. This is one. Here as it involves, so it produce H plus, remaining double bond CH2. Similarly, you can do another one. Here if second one is involved, so it will be H plus, then H, then double bond CH2, like this. 3. How many possible? Another one also possible. So as it has 3 CH bond which involves interaction with vacant p orbitals, so this molecule has 3 alpha hydrogen atom. As it has 3 alpha hydrogen atom, so 3 types of hyperconjugation is possible. And this hyperconjugation also called as no bond resonance. It is also called as no bond resonance, because involvement of CH bond during delocalization, the CH bond breaks, forming H plus. This H plus will be attached to the carbon atom of carbon-carbon double bond. It will not be free. That's why it is, we should think that it is not acidic. This hydrogen not acidic. This H plus is attached to the carbon. After loss of this CH bond, this bonded electron, the H plus just it will be fixed to the carbon-carbon double bond. So it is not free. As 3 alpha hydrogen atom here, so 3 types of structure, this type of no bond resonance is possible. So in this case, if you see this molecule O3C plus, as it has 9 alpha hydrogen atoms, So 9 alpha hydrogen atoms. So 9 alpha hydrogen atom means 9 hyperconjugation is possible, and with CH3 CH2 already discussed, and with this CH3 CH plus, here 6 alpha hydrogen atoms. So 6 resonance hyperconjugation or no bond resonance is possible. So as the number of alpha hydrogen atom is more, number of hyperconjugation will be more. So the stability order, if you see the stability order of carbocation, your tertiary greater than secondary, then which is coming primary, that is your primary, then methyl. This carbocation is least stable because it has no alpha carbon, it has no alpha hydrogen atom. That's why delocalization is very less. So least stable. This is least stable. This is related to stability of carbocation, tertiary greater than secondary, greater than primary, like this. And in other cases, also we can take that more substituted alkene. If you see the more substituted alkene, this alkene is more stable than this alkene, which is more stable than trans alkene, which is more stable than cis alkene, then which is more stable than 1-methyl, which is more stable than CH2 double bond CH2. Here the stability order. Here stability, why it is more stable? Because if you see, it has how many? 12 alpha hydrogen atom. As 12 alpha, this is alpha, this is alpha, this is alpha, this is alpha. Functional group, next carbon is alpha. Functional group, then next carbon is, this is the functional group, next carbon alpha. How many alpha? 1, 2, 3, 4. So each alpha carbon contains 3 hydrogens, so 12 alpha hydrogen, that means the hyperconjugation is more here. Here the number of hyperconjugation is 12. Here number of hyperconjugation is 9 alpha hydrogen atom. Here 6 alpha hydrogen atom. Here also 6. Here 3 alpha hydrogen atom. It has no alpha. That's why your this substituted, that is 1, 2, 3, 4. That means 2,3-dimethyl 2-butene. 2,3-dimethyl 2-butene is most stable alkene due to hyperconjugation because it is stabilized by involvement of CH bond from alpha carbon, forming pi bond conjugation. Then this bond breaks. So in this way, 12 types of alpha hydrogen atom available. So 12 number of alpha hydrogen means 12 number of hyperconjugating structure is possible. So stability is more. So this is the concept regarding the stability of alkene. And the third application is, third example is here CH3O3C. This carbocation is less stable than because you see here what happens. If you see, this is the benzene, and in terms of inductive effect, this is the inductive effect. But if you see hyperconjugation, here hyperconjugation will be less because no, this carbon, this position This you can say this alpha position, because when benzene ring, the next carbon, if this carbon contain hydrogen, then so for example, you can take this one, this case, this methyl group when attached to benzene ring, then what happens? It will be resonance like this. So the first structure will be H plus, then CH, then double bond, benzene ring like this, then like this, CH2. Okay, so by hyperconjugation, this CH bonded electron shifted towards CH2 plus. So stability increases. In this type, three alpha hydrogen atom available. 3 alpha hydrogen atom available. You can say it is alpha because attached to benzene. Next carbon is alpha. So that's why these 3 hydrogen involved in the formation of hyperconjugation, stability is more. But this case, stability is less because it has no hydrogen attached to carbon, because it is hydrogen separated by methyl group. That's why less stable, but it is more stable. So we have to remember in this way application of hyperconjugation. If number of hyperconjugation is more, stability is more. More hyperconjugation, more will be the stability. This concept is very important concept. More hyperconjugation, more will be the stability. So hyperconjugation is called as no bond resonance. Then last important effect, that is steric effect. What is steric effect? Steric effect means bulky. Steric means bulky. It is also called as trace. Some bigger size atoms or groups attached to the particular atom. Then due to the large size, the unavailability of space to accommodate in the particular atoms, that's why that is called steric effect. It is an influence on a reaction rate. Due to presence of this effect, it is influence on the reaction rate due to the presence of bulky groups. This is very important. Bulky groups means large size atoms or groups where the molecule occupies space. That means due to the presence of this bulky group, large size atoms, large size groups, it changes the reaction rate. It brings the change in the reaction rate, that is called steric effect. Due to presence of bulky group, it brings change in the structure. It brings change in structure and properties. These two things changes. Structure also change and properties also change. This is called steric effect due to presence of bulky group, large size atoms and groups. That is called bulky group. What are the examples of this? For first application, we can discuss that this alkene is less reactive than trans. This is called cis. This is called trans. And as cis position, the bulky group is that large size bulky groups methyl group does not allow the attacking of electrophile. Regarding electrophilic, electrophilic addition reaction. Already we have discussed. Electrophilic addition reaction is slow in case of cis because electrophile, when electrophile will be taken, electrophile attack to the pi bond due to presence of this bulky group. It cannot allow to attack this pi bond freely because due to large size atom groups available in the reactive side. During attack, at the attacking side, the bulkier groups are available. It does not allow the attacking of electrophile. That's why cis alkene is less reactive than trans alkene. This is very important thing related to what? Attacking of electrophilic addition reaction. Then second application of steric effect is, it is also called steric hindrance. Second application is, if you see esterification of this group, in presence of methyl, this group is more reactive towards esterification compared to this group. Esterification. This we are comparing esterification. What is esterification? Addition of alcohol and acid forming ester. Addition of alcohol and acid forming ester. This is acid when you add alcohol, it gives ester. This is also acid when you add alcohol, it gives also ester. But this acid is more reactive than second one because this group, the COH group is away from the bulkier group. This is your bulkier group. This COH position is more distance, far away from bulkier group. But this group is very closer to the bulkier group. That's why attacking of alcohol will be slow. This reaction will be slow due to presence of bulkier group closer to carboxyl group. But here the carboxyl group maintains some distance between the bulkier group. That's why this carboxyl group, this carboxyl acid is more reactive than this one because second one has steric effect. Second one has steric effect, more bulkier group attached, no space to attack by alcohol to the carboxyl group. That's why reactivity is slow. This is very important. You have to practice these examples. Then, if you see nitration of this group, with nitration, that sulfuric acid and nitric acid undergo nitration means NO2 plus will attack as electrophile. Aromatic compound shows electrophilic substitution reaction when nitration occurs, but this nitration always gives what? That only para position the product is formed. The product form only para substituted. Para product. Why para product is formed? Why the product is para substituted product, but why not ortho? And this group is ortho para directing group, but why only para product is formed? Why not ortho? Because ortho position is not free due to bulkier group. Due to bulkier group, ortho position, this is your ortho position, this is your ortho position, and this is your para position. Ortho position is not free due to this bulkier group. That's why electrophile attack to the which position? Para position. That's why product is para, not ortho product. Ortho product is very less. This is your more major product, and minor product is this is your minor product. If you see, If you see here nitro group, this position, this is minor, this is major, because this side is not free. This side is not free to attack electrophile at this position. That's why the major product is para-substituted product. Okay? Then complete this one. Next we will start. Third example we can take. Fourth one. This is your fourth example. Ketone is more reactive towards aldehyde this reaction we can say, suppose one nucleophile Cn minus, you take attacking of Cn minus, releasing this group. If you do, this is called nucleophilic addition reaction. This is called nucleophilic addition reaction. Already we have discussed. Ketone is less reactive. Reactivity is just opposite. Ketone is less reactive than aldehyde. Aldehyde is less reactive than formaldehyde. Why ketone is less reactive towards nucleophilic addition reaction? Because here what happens, this bulkier group present in ketone, this bulkier group, this sterically protected group does not allow the attacking nucleophile to the partial positive carbon, because CO bond is a polar bond, carbon carry partial positive charge, oxygen carry partial negative charge, but carbon partially positive carbon attacked by nucleophile. As this partially positive carbon is just covered by bulkier methyl group, so attacking will be slow due to covering of bulkier group around carbon. Then one bulkier group, reactivity is more. No bulkier group, reactivity is more reactive. More reactive towards nucleophilic addition reaction. This is very important concept regarding that reactivity. Then already you know, if you see CH3 whole 3 CCl towards your aqueous KOH, this reaction by SN2 mechanism, means one step mechanism. By SN2 mechanism if you do, it is slow, very slow. The product is CH3 whole 3 COH, but the reaction is very slow reaction. But same compound, if you take CH3Cl, same reactant if you use, the product will be faster. This reaction is faster, but this reaction is slow. Formation of alcohol from haloalkane to alcohol. This reaction from SN2 mechanism, nucleophilic substitution. Here nucleophile is OH minus. Already you know types of organic reactions. Here OH minus attack to carbon, then Cl is released. That is called nucleophilic substitution reaction. It is slow because this bulkier 3-methyl group do not allow freely, or they do not allow attacking of OH minus freely. So OH minus cannot attack properly to the carbon of this haloalkane because it is covered by 3-methyl groups. But it is free as it attaches to 3 hydrogen. Here this carbon attaches to 3-methyl group. So this carbon is somewhat free. So nucleophile OH minus can easily attack. That's why reaction is faster. So this is the example of sterical hindrance, that is steric effect of the particular group or group attached to the particular carbon. Similarly, we can take another examples. Phenol. Phenol is an acid, already you know. Phenol is an acid. this phenol, when attached to nitro group, phenolic character is more, but when it is attached to 3-methyl this position, it is less acidic compared to same phenol. If you take same phenol in this position, as nitro group is a attracting group, it is minus effect. This is minus effect, so acidic character is more. But this nitro group attached to bulkier group, so the attraction power, the minus effect of nitro group is collapse. So nitro group cannot attract properly due to the presence of two bulkier groups. So reactivity becomes slow. So the attracting nature, withdrawing nature of nitro group decreases due to the bulkier group attached to it. But here there is no bulkier group with NO2. So NO2 is free, so easily attract the electron. That's why acidic character, minus effect is more prominent. Here minus I effect is more, here my same group but minus I effect is less, minus I effect is less, here minus I effect is more. Why here minus I effect is less? Due to two bulkier group attached to nitro group. Here minus I effect is more because it is free. So this is some important application. Another application you can take, that very important, that tertiary amine in aqueous medium is less basic than primary amine, methyl amine. This is primary amine, this is tertiary amine. Tertiary in aqueous medium. In aqueous medium. In aqueous medium, tertiary is less basic character, less basic than methyl amine, that is primary amine, because 3-methyl group undergo repulsion, undergo steric effect, undergo steric hindrance with nitrogen group. Due to the steric repulsion between 3-methyl group around nitrogen, the cannot supply electron towards nitrogen due to sterically repulsion. That's why the basic character of nitrogen is less. Another thing we can also say, due to sterically protected of nitrogen group, the water cannot enter to the nitrogen. As water cannot enter to the nitrogen due to sterically protected, that's why tertiary amine is least basic compared to primary amine and secondary amine. So due to steric effect, the basic character is less. Due to steric effect, the reactive acidic character also less. So many factors are there. Due to steric effect, this reactivity is also less. So these are some important explanation of steric effect or steric hindrance. It is also called as that bulkier effect. It is also bulky effect or steric effect or steric hindrance. It is also called as that Van der Waals effect also we can tell, because due to the bulkier group, large size group, it hinders the reactivity. It brings the change in the structure and properties of the organic compound due to sterically protected group, more bulkier group. So these are very important effect in organic chemistry, and this effect that already we have discussed, indot effect, resonance effect, hyperconjugation effect, and electromagnetic effect and steric effect. You can apply this effect in different examples, and which effect is appropriate for which change in properties, you have to practice it. Then you draw the different structures, then you will have better knowledge regarding the change in properties of organic compounds and their comparison. Okay, thank you.